Welcome back, traveler. Tonight we step into a motion so familiar that it almost disappears from thought. Earth goes around the sun once every year, smoothly, reliably. It's one of the first facts we ever learn about space, often presented the same way a rule is presented. This is just how it works. The Earth moves, the sun sits there, and the year passes. Most of us carry that idea without friction. The Earth is held by the sun. Gravity pulls inward, motion keeps it from falling, and the balance produces an orbit. It sounds tidy, mechanical, finished, like a problem that's already been solved and filed away. But here's what most people don't realize. If Earth were only being pulled, it wouldn't orbit at all, it would fall. And if it were only moving forward, it would leave. The fact that it does neither means the situation is far stranger than a simple balance suggests, because hidden inside that familiar path are consequences we rarely connect to orbits at all. Time ends up behaving differently than our intuition expects. Space refuses to act like a passive stage. Now stops meaning the same thing everywhere. And motion becomes something you can never fully step outside of, no matter how fast or how far you travel. By the end of this journey, you'll understand not just why Earth orbits the sun, but why falling forever can look exactly like missing forever, why motion cannot be turned off, and why this single orbit quietly limits what the universe allows us to do. If you're enjoying these late-night explorations, like the video, subscribe, and leave a comment telling me where you're watching from and what time it is for you. Now, let's begin. For most of human history, the explanation felt straightforward because our everyday experience made it feel that way. When you throw a stone, it falls. When you stop pedaling a bicycle, it slows down. Motion fades unless something keeps pushing. So when people first tried to understand Earth's path around the sun, they naturally imagined a force doing the holding. Gravity pulls inward. Something else must be keeping Earth from dropping straight down. That intuition lingered for centuries because it works so well at human scale. You feel gravity as a downward tug. You feel motion as something that needs effort. Standing still feels natural. Movement feels temporary. And if you grow up inside that intuition, an orbit sounds like a fragile compromise, constantly on the verge of collapse. But that picture quietly breaks the moment you remove the ground beneath your feet. Imagine you're standing on a high tower and you drop a stone. It falls straight down, no mystery there. Now imagine you throw the stone forward as you drop it. It still falls, but it also moves sideways. The faster you throw it, the farther it travels before hitting the ground. This still feels ordinary, it's just falling plus forward motion. Now stretch that idea a little further. Imagine throwing the stone so fast that the ground curves away beneath it as it falls. The stone keeps falling, but it never hits the ground. It keeps missing. Not because gravity stopped pulling, but because the surface beneath it keeps dropping away at the same rate. That, at its core, is an orbit. Earth is not being held up by motion. It is falling, continuously, toward the sun. The only reason it doesn't crash is that it's moving sideways fast enough to keep missing. The sun is not suspending Earth. It is pulling it inward relentlessly, and Earth responds by never quite arriving. Both are happening all the time. The orbit exists because neither wins. And here's where intuition starts to crack. If Earth is falling, then down doesn't mean what you think it means. There is no single downward direction. Down always points toward the sun, but Earth is moving sideways relative to that direction, constantly redefining what down even is. This means an orbit is not a path laid out in advance. It is a negotiation that updates every instant. Gravity changes the direction of motion. Motion changes where gravity points next. The curve you imagine is not drawn ahead of time. It is traced out moment by moment. That's already strange enough. But it gets stranger when you ask the next obvious question. Why does Earth have that sideways motion at all? Gravity explains why Earth doesn't move in a straight line. It does not explain why Earth wasn't at rest to begin with. If the sun formed first and Earth appeared later, why didn't it just fall straight in? This is where the old intuition quietly collapses. Earth did not start from stillness. Nothing did. Long before there was an Earth, before there was even a sun in the familiar sense, there was a cloud of gas and dust moving through space, not drifting neatly, but swirling, colliding, tugged unevenly by surrounding matter. Every particle carried motion, not organized motion, just leftover motion that never quite canceled out. When that cloud collapsed under gravity, it did not erase that motion. It concentrated it. This is the same effect you see when an ice skater pulls their arms inward. They don't stop spinning. They spin faster, not because something added energy, but because the same motion now has less space to spread out. As the solar system formed, motion that once belonged to a vast, diffuse cloud was squeezed into a smaller and smaller region. What had been gentle drift became structured rotation. A disk formed. Everything inside it shared a general sense of direction. Earth's sideways motion is not something it acquired later. It is something it inherited. This reframes the orbit entirely. Earth is not circling the sun because it found a stable compromise after the fact. It is circling because it was never given the option to fall straight down. The sideways motion came first. Gravity merely curved it, and that raises a problem. If motion came first and gravity only bends it, then an orbit is not a special state. It's what happens when you fail to remove motion completely. Falling inward is the special case. Orbiting is what happens when erasure fails. At first, that sounds backwards, but once you see it, you can't unsee it. Standing still is not the natural state of the universe. Motion is. We only experience rest because friction, air resistance, and contact with the ground bleed motion away. Space has none of that. Once something is moving, it keeps moving unless something actively interferes. Gravity doesn't interfere by stopping motion. It interferes by redirecting it. So Earth orbits the sun not because it is delicately balanced, but because nothing ever removed the motion it already had. And this has consequences that reach far beyond Earth. If motion cannot be turned off, then there is no such thing as absolute rest. You can slow relative to one thing only by speeding up relative to another. You can fall toward the sun only because you were already moving sideways. You can never step outside motion itself. This is why every attempt to imagine a natural frame of rest fails. No matter where you go, something else is moving relative to you. The Earth moves around the sun. The sun moves through the galaxy. The galaxy moves relative to others. There is no final background where motion stops. Earth's orbit is your first encounter with that idea, disguised as something familiar, and that leads to a deeper puzzle. If Earth is always falling and always missing, then what does it even mean to say it is going around the sun? Is the orbit something real, or just a description of constant failure to collide? That question doesn't just challenge geometry. It challenges the way we think about forces, motion, and what it means for something to be stable. Because if an orbit is just falling forever, then stability is not about staying still. It's about moving in the right way. And that realization opens the door to something far larger than Earth and the Sun. It forces us to ask whether gravity is really a pulling force at all, or whether something deeper is shaping the path Earth follows through space. That's where the story takes its next turn. That turn begins when you stop thinking of gravity as a hand reaching out and start thinking of it as a rule about how motion is allowed to unfold. The idea that gravity is a pull is intuitive because it matches what you feel. You drop something, it accelerates downward, and the sensation is unmistakable. For centuries, that feeling guided how people imagined the cosmos. Massive things attract smaller things. The sun pulls on Earth. Earth responds by curving its path. End of story. But there's a quiet mismatch hiding in that explanation. If gravity was simply a pulling force acting across empty space, then motion and rest would still be fundamentally different states. Something would have to be actively pulled out of rest. Something would have to be held in motion to keep going around. Orbits would be dynamic standoffs between competing influences. Yet when you look closely, none of that is actually required. Imagine you're inside a train moving smoothly at constant speed. You toss a coin straight up. It comes straight back down into your hand. Nothing about the motion of the train seems to matter. The coin doesn't drift backward. It doesn't lag behind. Inside the train, motion has disappeared. Now imagine the train starts to curve gently to the right, following a long, smooth bend in the tracks. You toss the coin again. From your perspective, something strange happens. The coin no longer falls straight back into your hand. It drifts sideways as it comes down, even though you didn't push it that way. Did a new force act on the coin? From outside the train, nothing mysterious happened. The coin continued moving straight, while the train curved underneath it. From inside the train, though, it looks like the coin was pulled sideways by something invisible. This is the first crack in the force-based intuition. Sometimes what feels like a force is really just geometry revealing itself from the inside. Now scale that idea up. Earth is not sitting in space while a force pulls it inward. Earth is moving through space that does not behave like a flat, power and passive stage. The presence of the sun changes the rules of motion themselves. Paths that would have been straight in empty space become curved when massive objects are present. From Earth's perspectives, it feels like gravity pulling inward. From a deeper perspective, Earth is simply following the straightest possible path available to it, one that bends because space itself is no longer flat. This is not a poetic metaphor. It is a precise shift in how motion is understood. In this picture, Earth is not constantly being yanked toward the sun. It is coasting freely, obeying inertia, while the geometry of space-time guides its trajectory. The orbit is not a compromise between pull and motion. It is motion, uninterrupted, taking place in a curved environment. At first, this sounds abstract, but it becomes clearer if you return to something tangible. Imagine rolling a marble across a stretched rubber sheet. If the sheet is flat, the marble travels in a straight line. Now place a heavy ball in the center. The sheet dips. Roll the marble again. Its path curves, even though you didn't push it sideways. The marble is still following the straightest available path. The surface just isn't flat anymore. Earth's orbit works the same way, except the surface is space and time themselves. And here's the unsettling implication. If gravity is geometry, not force, then Earth is not being kept in orbit by constant effort. It is doing exactly what free motion allows in the presence of mass. There is no tug of war. There is no balance to maintain. The orbit is not fragile. It is natural. This explains something that force-based intuition struggles with. Why doesn't Earth slowly spiral inward as it loses energy to gravity? Why doesn't the sun have to constantly pull harder to keep Earth from escaping? Why does the orbit persist without correction? Because nothing is being spent. Earth is not climbing out of a gravitational well each time it completes an orbit. It is not fighting gravity. It is inhabiting the shape gravity creates. And this changes the meaning of falling. To fall is not to be pulled. It is to follow the natural geometry of space-time when nothing prevents you from doing so. Astronauts in orbit are not weightless because gravity disappeared. They are weightless because they are falling freely, together along the same curved paths. Earth is doing the same thing, which brings us back to the original question. Now transformed, why does Earth orbit the sun? Because it is moving freely through a curved universe, carrying motion it never lost, along paths shaped by mass it cannot ignore. And that answer forces another question into view. If Earth's orbit is not a balance but a free path, if gravity is not a pull but a structure, then what, exactly, would it mean for Earth to stop orbiting? Not hypothetically. Physically, what kind of change would be required to take Earth off that path? The answer is not remove gravity. It is not add force. It is far more drastic. You would have to change the geometry itself. And that realization quietly raises the stakes of everything that follows. Because if orbits are expressions of space-time's shape, then leaving them is not just a matter of effort. It is a matter of rewriting the environment you are embedded in. And that is where the explanation stops being about Earth and the sun, and starts being about the limits of motion, freedom, and escape in the universe itself. To understand those limits, it helps to ask a question that sounds simple but isn't. What would it actually take for Earth to stop orbiting the sun? The instinctive answer is more force. Push it harder, pull it away, give it a shove in the opposite direction. But once you've reframed an orbit as free motion through curved space, that answer stops making sense. You don't cancel a path by pushing against it. You leave it by changing the conditions that define it. Imagine again that train following a long, gentle curve. Inside, the sideways drift of the coin felt like a force. From outside, it was just geometry. If you wanted the coin to stop drifting, you wouldn't push the coin harder. You'd straighten the tracks. Earth's orbit is the same. As long as the sun's mass shapes space the way it does, Earth will keep tracing the same family of paths. You can add energy to Earth and change which path it follows. You can stretch the orbit into a wider ellipse. You can even give it enough energy to escape entirely. But at no point are you turning off the orbit. You're selecting a different route through the same curved landscape. This is why escape velocity has the meaning it does. It isn't the speed needed to overpower gravity in a tug of war. It's the speed needed to choose a path that never loops back. A path that curves, yes, but not enough to remain bound. And here's where the intuition breaks again. Earth does not orbit the sun because it lacks the energy to leave. It orbits because the energy it has is precisely the energy it inherited. the energy of motion that came with it from the beginning. Gravity didn't put Earth in orbit. Gravity shaped the environment in which that inherited motion plays out. Which means the real question isn't, why does Earth orbit? It's, why does Earth have this motion at all? And we're back where we started, but now with sharper tools. Earth has sideways motion because the material that became Earth was never at rest. The solar system formed from a rotating disk. Earth condensed within that disk, already moving. When it became a planet, it didn't suddenly acquire a new trajectory. It continued the one it was already on. The orbit didn't begin when Earth formed. It was already happening. This is why the Sun did not need to capture Earth. Capture implies a transition from free to bound motion. Earth never made that transition. It was born bound. Born moving. Born inside a geometry that made looping paths the default outcome. And that realization dissolves another quiet misconception. We often imagine gravity as something that reaches out across space, grabbing hold of objects and pulling them in. But in reality, gravity defines a structure that objects are already inside. You don't get caught by it later. You grow up within it. Earth did not fall into orbit. It matured into one, and that has a subtle consequence for how we think about stability. If orbits are free paths, then stability is not about constant correction. It's about the absence of disruption. As long as nothing dramatically alters Earth's energy or the Sun's mass, the path persists, not because it's protected, but because nothing compels it to change. Change only happens when something external intervenes, a close encounter. A massive redistribution of energy, a geometric shift large enough to matter. This is why the solar system feels so calm, not because it is static, but because it is undisturbed. And this calmness hides how demanding change actually is. To meaningfully alter Earth orbit, you would need to inject or remove an enormous amount of energy, not a push, but a sustained redirection. Not a momentary force, but a rewriting of motion inherited from billions of years ago. That energy doesn't come cheaply. This is why even imagining planetary engineering feels fantastical. It's not that physics forbids it outright. It's that the scales involved dwarf anything we can realistically manipulate. Earth's orbit is not a fragile arrangement waiting to be nudged. It is a massive yet a conserved trajectory embedded in the structure of space-time itself, which brings us to an unexpected place. Earth orbits the Sun, not because it is trapped, but because it is free to move the way motion moves when nothing stops it. Free to follow the straightest path available in a curved universe. Free to continue what it started doing long before it became a planet at all. And that freedom has a cost. Freedom in physics does not mean flexibility. It means commitment. Once motion exists and geometry is set, freedom means following through. There is no undo button, no return to stillness, no neutral ground to step back onto. You are either moving along a path, or you are changing the environment that defines it. So when you stand on Earth and think of it circling the Sun, it's tempting to imagine a central force holding you in place. Something keeping you from flying off into space. But the deeper truth is the opposite. Nothing is holding you here. You are moving with Earth because Earth is moving. You are falling with it, freely, along a path shaped by mass and history. The ground beneath you exists because that motion persisted long enough for a planet to cool, solidify, and build layers. And that perspective changes the emotional texture of the orbit. It's no longer a cage. It's no longer a balance. It's a continuation, the continuation of motion that never stopped, shaped by geometry that never asked permission, carrying a world along a path that feels stable only because it has been stable for longer than memory. Earth orbits the sun because the universe does not erase motion. It bends it, it redirects it, it lets it run. And once you see that, the orbit stops being a fact you memorize and becomes something you inhabit. A quiet, continuous fall through a curved universe, so smooth and persistent that it feels like standing still. That's not the end of the explanation, but it is the point where the question stops being about why in the ordinary sense and starts being about what kind of universe makes such a thing inevitable. And that is where the story deepens again. That deeper question isn't answered by adding more detail. It's answered by changing what you think an answer is supposed to look like. When people ask why Earth orbits the sun, they often expect a cause in the ordinary sense. A push, a pull, an event that happened and then stopped. But the orbit is not the result of something that happened once. It is the result of something that never stopped happening. Motion. Earth is not responding to gravity in the way a ball responds to a shove. It is responding the way a sentence responds to grammar. The rules are not acting on it from the outside. They are defining what counts as a valid continuation. In flat, empty space, the valid continuation of motion is a straight line. Near the sun, the valid continuation curves. Earth does not need to be told to follow that curve. There is no instruction being sent across space. There is only one path that remains consistent with how space and time are shaped. This is why the orbit feels inevitable once it exists. Not because it was inevitable that Earth would end up here, but because once it did, the continuation stopped being optional. That distinction matters. The universe is full of things that were not inevitable, but became unavoidable once they happened. The orbit is one of them. It did not have to exist, but once it did, it locked itself into the future. And that tells you something subtle about explanation itself. In everyday life, we explain things by pointing to causes in the past. But in physics, especially at large scales, explanations often point to constraints that extend into the future. Not "this happened because of that," but "this continues because there is no alternative that fits." Earth orbits the sun because, given the motion it has and the geometry it inhabits, there is no other way for it to move that does not require a massive disruption. The orbit is not maintained, it is permitted. And that reframes stability one last time. Stability is not the absence of change. It is the absence of contradiction. As long as Earth's motion and the sun's mass do not contradict each other, the path persists. Change would require contradiction, energy injected in the wrong way, geometry altered beyond tolerance, history overwritten rather than extended. None of that has happened. So the orbit continues, not because something is holding it together, but because nothing has come along that forces it apart. This is why the most accurate description of Earth's orbit is also the simplest. Once you see it clearly, Earth keeps going because it was already going. Gravity does not stop that going, it shapes it. Space-time does not resist motion, it organizes it. And you are part of that organization. You feel weight not because Earth is pulled inward, but because the ground prevents you from following the same free path Earth follows around the sun. The sensation you call gravity is the feeling of being stopped from falling the way the planet falls. That is a strange thing to realize late at night. You are not standing on a stationary world while forces act at a distance. You are riding a moving world that is constantly falling, constantly missing, constantly continuing. The orbit is not happening somewhere out there. It is happening everywhere you are. And that finally resolves the question in the only way it can be resolved, without oversimplifying it. Earth orbits the sun because motion was never removed, because space is not flat, because geometry guides what motion is allowed to do, and because once a path exists that satisfies all of that, the universe has no reason to replace it with another. Not because of balance, not because of holding, not because of force in the way we usually imagine it, but because this is what free motion looks like in a universe shaped by mass and history. The Earth is not circling the sun like a stone on a string. It is falling freely through a curved reality, carrying you with it, year after year, so smoothly that the motion disappears into habit. And when something disappears into habit, it's easy to forget how strange it really is. That's why this question keeps coming back. Not because it hasn't been answered, but because the answer quietly changes what it means to be standing still. That quiet change in meaning is the last piece most explanations leave untouched. We grow up thinking that stillness is the default, and motion is the exception. That rest is natural, and movement needs explanation. But the orbit turns that idea inside out. It shows you a universe where motion is the given, and stillness is what requires force, structure, and resistance. Earth feels still because you are moving with it. You are moving sideways around the sun at extraordinary speed, while also moving with the sun through the galaxy, while the galaxy itself drifts among others. None of that registers in your body, because motion without acceleration leaves no trace in your senses. You only feel change, not movement itself. That is why orbits are so deceptive. They hide motion inside continuity. If Earth were suddenly to stop orbiting, you would feel it instantly, not as calm, but as catastrophe, because stopping would require an immense acceleration, a violent intervention that would tear apart oceans, crust, and atmosphere. The reason you don't feel motion now is not because it isn't there, but because nothing is trying to stop it. This is the final inversion of intuition. Earth does not orbit the sun because something is constantly acting on it to keep it there. Earth orbits the sun because nothing is acting on it strongly enough to prevent it from continuing. Gravity is not fighting motion, it is shaping its permission. Once you accept that, the question, why does Earth orbit the sun, stops asking for a cause in the past and starts asking about constraints in the present. It becomes less about what happened long ago and more about what is allowed to keep happening now. Earth orbits because its motion and the sun's mass are compatible, because space-time shaped by the sun allows looping paths, because Earth's inherited velocity fits inside that shape without contradiction. And compatibility is a powerful idea. It explains why some systems persist while others collapse, why some motions repeat while others explode into chaos, why the universe can be dynamic without being unstable. The orbit is a compatibility between motion and geometry. Break that compatibility, and the orbit ends. Not gently, not symbolically, but physically, through energy transfer so large it rewrites the system. Until then, the path remains the same kind of path, year after year, not because it is enforced, but because it works. This is why the explanation ultimately feels unsatisfying. If you are expecting a single cause, there is no lever to point to. No moment where the universe decided, this shall be an orbit. There is only a process that allowed motion to continue in the presence of mass, and that process never turned off. Earth orbits the sun because the universe did not give it the reason to do anything else. That answer is subtle enough to feel evasive, but it is actually more demanding than a simple force story. It requires you to accept that the universe explains itself not through commands but through permissions, not through active holding, but through the absence of obstruction, and that has consequences for how you think about freedom, change, and limits. In physics, freedom does not mean you can go anywhere. It means you will keep going unless something stops you. Limits are not fences, they are shapes. They define which paths exist and which do not. Earth's orbit is one of the paths that exists. It exists because of motion inherited from formation, because of curved space-time shaped by the sun, and because nothing has intervened strongly enough to invalidate that combination. That is all, and that is enough. When you step back and look at it this way, the orbit stops being a special trick of gravity and becomes an example of a deeper rule. The universe is built to carry motion forward, not erase it. That rule shows up everywhere, in planets, in stars, in galaxies, in the way time refuses to run backward, in the way history accumulates instead of resetting. Earth orbiting the sun is not an isolated phenomenon. It is the local expression of a universe that remembers motion, and you live inside that memory. Every sunrise you experience is not just Earth turning, it is Earth continuing. Every year that passes is not a loop closing, it is a path extending, nearly repeating, but never exactly the same because nothing ever retraces itself perfectly. The orbit feels circular. The reality is a slow spiral through time. That's why this explanation doesn't end with a neat definition. It ends with a perspective. Earth orbits the sun because motion persists, because space is shaped by mass, because compatibility matters more than balance, and because once a path exists that satisfies those conditions, the universe allows it to continue without interference. Not held, not balanced, not trapped. Just moving, freely, relentlessly, and with no reason to stop. And once you see that, the question no longer feels like something you need to answer again. It feels like something you are already part of. The paradox only feels sharp because the word fall is doing more work than it's allowed to do. When you picture falling, you imagine a direction, down, toward the ground, toward an end. Falling in everyday life always has a destination, a floor, a surface, a moment where motion stops and something collides. That intuition is so deeply wired that we don't notice it anymore. We don't ask what falling is. We ask why it didn't finish. So when you look at Earth and the sun and ask why Earth doesn't fall, what you're really asking is why the fall never ends. And that's the trap. Because falling is not defined by impact. It's defined by motion under gravity. The impact is optional. The motion is not. Imagine standing on a cliff and dropping a stone. It accelerates downward. That's falling. The moment it hits the ground is not part of the fall. It's the interruption of it. Now remove the ground, the stone doesn't stop falling. It just keeps going. That sounds obvious until you actually follow the idea all the way through. If there is no surface to hit, no floor to collide with, no point where motion is forced to stop, then falling becomes something very different. It stops being a transition and becomes a state a continuous condition rather than an event. This is the key shift the thumbnail is quietly demanding. Earth is not failing to fall into the sun. Earth is falling into the sun, constantly, and never being interrupted. To see why this doesn't look like falling, you have to give up the idea that falling means straight down. There is no straight down in space. Down only exists relative to something, a surface, a reference, a place where motion ends. In orbit, there is no such reference. Gravity points toward the sun, but Earth's motion never lines up with that direction long enough to arrive. It keeps missing. Not missing because gravity is weak, not missing because motion is resisting gravity, but missing because motion is already there. Take the simplest possible picture. Throw a stone forward. It falls and moves sideways. Throw it harder. It falls for longer before it hits the ground. Throw it even harder, and the ground curves away beneath it. The stone keeps falling, but the surface never arrives. Nothing magical happened. You didn't cancel gravity. You didn't balance forces. You just failed to remove sideways motion. That failure is the orbit. Earth is doing the same thing, just with no ground to ever catch up. From one moment to the next, gravity pulls Earth inward. Earth responds by changing direction slightly. Then gravity pulls again toward a new direction. Earth responds again. At no point does gravity stop acting. At no point does Earth stop falling. The orbit is not drawn ahead of time. It is stitched together from endless tiny failures to collide. This is why the red circle on the thumbnail feels unsettling. It marks a place where, intuitively, the fall should be obvious. Where Earth looks like it's being dragged inward, where you expect something dramatic to happen, but nothing does, because nothing ever does. There is no special point in the orbit where Earth is more likely to fall, no dangerous diction, no unstable stretch. Every point is the same kind of fall, just aimed slightly differently. And here's where the intuition breaks completely. If Earth were to stop falling, that would be the strange event. Stopping would require an interruption, a surface, a force that removes motion instead of redirecting it, a kind of cosmic break. Gravity cannot do that. Gravity only curves. It never erases. This is why asking, "Why doesn't Earth fall?" is like asking why a thrown stone doesn't stop mid-air and drop straight down. It already is dropping. The sideways motion just hasn't been taken away, which raises an uncomfortable realization. If falling is continuous and impact is optional, then the thing we call rest is not the natural state. It is the artificial one. Rest only exists where motion is constantly being destroyed by friction, by collisions, by contact. Space has none of that. So when you imagine Earth orbiting peacefully, what you're actually seeing is the absence of interruption, a fall that has been allowed to continue uninterrupted for billions of years. That uninterrupted fall is so smooth, so regular, so predictable, that your brain refuses to label it as falling at all. It feels like stability, but stability here does not mean stillness. It means consistent motion. This is the heart of the paradox the thumbnail is pointing at. Earth doesn't fail to fall because it's balanced. It doesn't fail because gravity is weak. It doesn't fail because something is holding it up. It fails because nothing ever removed the motion it already had. And once you see that, a deeper question starts to form. If Earth is falling freely, and astronauts in orbit are falling freely, and satellites are falling freely, then what does it actually mean to feel gravity? Why do you feel heavy while Earth does not? Why does falling feel like weightlessness in space, but heaviness on the ground? That question cannot be answered by talking about orbits anymore. It requires turning the entire picture upside down and asking whether gravity is something you feel when you fall, or something you feel when you are prevented from falling. That's where the story goes next. There's a reason the idea of constant falling feels wrong in your body. Right now, wherever you are, you probably feel heavy, solid, anchored. Your feet press into the floor. The chair presses into your back. Your body insists that gravity is pulling you downward, hard enough that rest feels earned. But here's the uncomfortable truth. That feeling has nothing to do with falling. It is the feeling of being stopped. Earth, in orbit, does not feel heavy. Astronauts do not feel heavy. Satellites do not feel heavy. Not because gravity is absent, but because nothing is preventing their fall. They are free to follow the path gravity allows. You are not. The difference between you and Earth is not gravity. It is the floor. Gravity is pulling you toward the center of the Earth right now, exactly the same way it pulls the Earth toward the sun. But unlike Earth, you cannot follow that path. The ground interrupts it. The floor pushes back. Your body compresses. Atoms resist being squeezed into the same space. That resistance is what you feel. If the floor vanished beneath you, the sensation would disappear instantly. Not slowly, not gradually, immediately. You would become weightless, not because gravity stopped, but because nothing would be stopping you. This is the same reason astronauts float. They are not beyond gravity's reach. In fact, gravity where they orbit is only slightly weaker than it is on Earth's surface. They float because they are falling freely, together with their spacecraft, along the same curved path. No interruption, no resistance, no weight. Weight, then, is not the presence of gravity. Weight is the presence of opposition. This is why the experience of gravity is so misleading. It teaches you the exact opposite of what is happening. Your senses tell you that gravity is the force pulling you down, when in reality what you feel is the ground pushing you up. The force you feel is not gravitational at all. It is electromagnetic. It is the force of atoms refusing to overlap. The floor is holding you away from the path gravity is trying to give you. Earth doesn't feel heavy because nothing is holding it up. This inversion matters. It means that falling is not what produces weightlessness. Falling removes weight. It is not falling that produces weight. And once you accept that, gravity stops behaving like a conventional force in your mind. It starts behaving like a property of motion itself. A rule about how paths curve when mass is present. This is why an orbit is indistinguishable from free fall from the inside. If you were sealed inside a windowless room orbiting the sun, you could perform every experiment you like. Toss objects, pour liquids, release particles, and none of them would reveal gravity acting on you. Everything would behave as if gravity were gone. Yet from the outside, gravity is acting constantly. The difference is not physical, it is experiential. Gravity is something you infer from deviation, not something you feel directly. And that brings us back to Earth's orbit with sharper clarity. Earth doesn't fall into the sun because nothing is stopping it from falling the way it already is. There is no surface, no resistance, no interruption, only continuous motion redirected endlessly. The moment Earth did stop falling freely, the moment something tried to hold it in place, that would be the catastrophe. So the paradox dissolves. Earth doesn't need to be supported. It doesn't need to be balanced. It doesn't need to be held. It only needs to be uninterrupted. And it has been uninterrupted for billions of years. Which leads to the next unavoidable question. If gravity is not something you feel when you fall, if weight comes from being stopped, then what does rest even mean in a universe like this? Is anything ever truly at rest? That question pulls us one layer deeper, and that's where the next block begins. The word rest feels solid, comfortable, like a place you can arrive and stay. You sit down, you stop moving, you rest. At least, that's what it feels like. But the moment you take the idea seriously, it starts to unravel. Because nothing about your situation actually changed. Your muscles relaxed. Yes, your effort stopped, but your motion did not. You are still moving. You are moving with the earth as it turns beneath you. You are moving with the earth as it orbits the sun. You are moving with the sun as it travels through the galaxy. And the galaxy itself is not parked anywhere permanent. Rest, it turns out, is not a physical state. It is a relationship. When you say you are at rest, what you mean is that you are not accelerating relative to your immediate surroundings. Your chair is not sliding away from you. The floor is not moving under your feet. Everything nearby agrees on how motion should behave. That agreement is what feels like stillness. But agreement is not the same thing as absence. This is why orbits are so misleading. From Earth's perspective, the sun appears to move across the sky in a regular pattern. From the sun's perspective, Earth traces a looping path. From a different frame, both are moving through space together. None of these views is more correct than the others. There is more master frame where motion disappears. This is the quiet lesson hidden inside Earth's orbit. The Earth does not orbit the sun instead of being at rest. It orbits because rest was never an option to begin with. If you imagine stripping away every reference point, no floor, no walls, no nearby objects, motion loses its meaning entirely. There is no speed without comparison, no still without something else moving. The universe does not provide a background grid to measure yourself against. It only provides other things. This is why gravity feels so strange once you see it clearly. It does not pull objects toward a fixed center in an otherwise static space. It curves the relationships between moving things. It changes how paths compare to one another. Earth's orbit is not Earth moving through space toward the sun. It is Earth and Sun participating in a shared structure of motion, and that structure has no natural resting place. You might think the center of the Sun is a candidate. Surely that is rest, but even the Sun is moving. It wobbles slightly in response to the planets. It travels through the galaxy. It carries inherited motion from its own formation. There is no cosmic chair to sit in. Which means the feeling of rest you experience is something created locally, not globally. It is enforced by contact, by surfaces, by resistance. When the ground holds you up, it forces you into a shared frame with the Earth's surface. It constantly adjusts your motion to match the planet's rotation and orbit. That constant adjustment is what you feel as weight and stillness. Remove the ground, and that coordination vanishes. This is why astronauts feel weightless, and also why they never feel at rest. Inside a spacecraft, there is no floor holding them into a shared frame. Everything floats. Everything drifts. Motion becomes obvious again. Earth's orbit is the ultimate version of this. The entire planet is in free fall. Nothing is holding it still. There is no larger floor beneath it, so its motion never turns into weight. And this reveals something subtle but profound. The universe does not privilege stillness. It tolerates it only where forces actively destroy motion, where friction exists, where collisions happen, where energy is bled away. Space has none of that. So in space, motion persists, paths extend, orbits form. Falling never ends unless something interrupts it. This is why asking why Earth doesn't fall into the sun is the wrong question. The correct question is, what could possibly stop it from falling the way it already is? And the answer is uncomfortable, almost nothing. To stop Earth's orbit, you would need to remove its sideways motion. All of it, not reduce it, not redirect it. Remove it. You would need an interaction so violent that the planet would not survive the attempt. Rest, in the cosmic sense, is catastrophic, which brings us to a final inversion. The reason Earth feels safe is not because it is at rest. It feels safe because it is moving smoothly. The danger is not motion. The danger is interruption. And once you see that, you realize that the universe is not a place where things sit and occasionally move. It is a place where things move and occasionally are forced to stop. Earth orbits the sun because nothing ever forced it to stop moving in the way it already was. And you, right now, only feel still because the ground is constantly doing that work for you. Remove it, and you would join Earth, not in chaos, not in acceleration, but in the same quiet, uninterrupted fall. A fall so consistent that it looks like rest. That realization leaves us with one last layer to peel back. If motion is the default, if rest is artificial, and if orbits are simply free motion allowed to continue, then the universe is not holding Earth in place at all. It is letting it go. And that is where the explanation reaches its deepest point. Once you let go of the idea that Earth is being held in place, a different question takes its place. If nothing is supporting the orbit, if nothing is actively maintaining it, then why doesn't it fade? Why doesn't Earth slowly lose its motion and spiral inward? Why doesn't the path decay the way movement decays in everyday life? The answer lives in a principle so familiar that we almost forget how radical it is. Things keep doing what they're already doing, not because they want to, not because something tells them to, but because stopping requires intervention. In everyday life, motion feels temporary because something is always interfering. Air resists, surfaces scrape, engines heat up, energy leaks away into sound, vibration, friction. We grow up in an environment where motion is constantly being erased, so we learn the wrong lesson. We learn that movement requires effort, that stillness is natural, that persistence is rare. Space teaches the opposite. Imagine a car on a perfectly frictionless road. No air, no bumps, no losses. You give it a single push. It accelerates briefly, and then it keeps going forever. Not slowing, not stopping. Not because of magic, but because there is nothing left to remove the motion you gave it. That situation feels unrealistic because we never experience it, but the solar system does. Earth is not being dragged around the sun by gravity. Gravity is not a motor. It does not provide energy. It only changes direction. The speed Earth already has, the sideways motion, is not replenished each orbit. It is conserved. This is the quiet dominance of inertia. Inertia is not laziness. It is loyalty. Objects remain faithful to the motion they already possess, unless something forces them to betray it. Earth has been loyal for billions of years. When the solar system formed, motion was not optional. The collapsing cloud carried angular momentum. That momentum was not destroyed. It was reorganized, concentrated, shared. Earth inherited its portion of that motion, the moment it condensed out of the disk. And nothing since has been powerful enough, persistent enough, or misaligned enough to take it away. So the orbit persists. Not because gravity keeps pulling Earth sideways, it doesn't. Not because Earth is being balanced delicately, it isn't. But because the sideways motion has nowhere to go. This is why orbits are stable without being rigid. Gravity bends the path inward. Inertia carries it forward. Neither cancels the other. Neither exhausts the other. They coexist without negotiation. And this coexistence explains something subtle about the shape of Earth's orbit. If gravity vanished instantly, Earth would not freeze in place. It would fly off in a straight line, tangent to its orbit, carrying all of its motion forward. If inertia vanished, if motion could simply be erased, Earth would fall straight into the sun. The orbit exists between those two extremes, but not because it's balanced between them. It exists because both are allowed to operate fully. Gravity does its job. Inertia does its job. Nothing interferes. This is why the orbit feels effortless. The universe is not spending energy to keep Earth going. It spent energy long ago, during formation, and then stopped spending. Everything since has been accounting, not expenditure. And that distinction matters. A system that requires constant correction is fragile. A system that runs on conservation is resilient. Earth's orbit is resilient because it is cheap. It costs nothing to maintain. The universe prefers cheap solutions. This is one of the deepest selection pressures in physics. Structures that require constant input vanish. Structures that persist without effort remain. Stars burn fuel. Orbits do not, which is why orbits outlive stars. And this returns us to the paradox in its most stripped-down form. Earth doesn't fall into the sun because falling does not remove motion. Earth doesn't drift away because nothing adds motion. The path it follows is the path that requires the least intervention, and the universe at every scale tends to preserve what does not require intervention. This is not design, it is accounting. Motion is conserved. Energy is conserved. History is conserved. The orbit is history in motion. Once you see inertia this way, Earth's orbit stops feeling like a special case and starts feeling like a local expression of a universal rule. Everything that can keep going will, until something stops it. And in the vacuum of space, stopping is the rarest event of all. That realization sets the stage for the next layer of the story. Because if inertia preserves motion and gravity shapes paths, then the orbit is not just a path around the sun. It is a record, a preserved trajectory from the moment the solar system learned how to move, and that record has consequences far beyond Earth. That's where we go next. Once you understand that Earth's orbit continues because nothing removes its motion, another layer quietly reveals itself. That motion had to come from somewhere, and whatever its origin was, it did not vanish. It did not fade. It did not reset when Earth became solid, when oceans formed, or when life appeared. It is still here, moving. Earth's orbit is not just motion, it is preserved motion. In other words, it is a memory, not memory in the human sense, not recollection or awareness. But physical memory, the kind that exists whenever a system keeps doing something because nothing erased the reason it started. Imagine dragging a heavy object across soft ground. Long after the object is gone, the tracks remain. Not because the ground remembers intentionally, but because the forces that made the marks were never undone. Now imagine those tracks never faded. That is what an orbit is. The solar system formed from a cloud that was not perfectly still. That imperfection mattered. A slight preference in motion, a tiny imbalance, became rotation. Rotation became a disk. The disk became planets. At no point did the system pause and reset. Every step carried the previous one forward. So when Earth moves around the Sun today, it is not responding to a current decision. It is honoring an old one. A decision made when neither Earth nor Sun existed in their present forms. The orbit is a fossil, but unlike rocks in the ground, it is a fossil that never stopped moving. This is why orbital properties are so revealing to astronomers. Direction, shape, tilt, speed. None of these are random. Each one encodes something about how the system began, what it interacted with, and what it avoided. Change the early conditions slightly, and the memory would look different. A more violent formation would leave more eccentric orbits. A disrupted disk would leave misaligned paths. A close stellar encounter would leave scars in inclination. Our solar system carries relatively clean memories. Earth's orbit is nearly circular, calm, predictable. That calmness is not generic, it is informative. It tells us that Earth formed in a disk that was stable, coherent, and undisturbed for a long time. It tells us that nothing later came along to erase or overwrite that structure. The past, once again, refused to let go. This is a broader rule than it first appears. Spin is memory. Orbit is memory. Alignment is memory. Whenever you see a large system doing something consistently, you are looking at preserved history. And preservation is selective. The universe forgets aggressively when it can. Collisions randomize motion. Friction converts it into heat. Turbulence scrambles direction. But where those erasers are weak or absent, memory persists. Space is a place where erasers rarely work. That is why cosmic structures can carry their past forward for billions of years. That is why galaxies rotate. That is why stars orbit galactic centers. That is why Earth keeps tracing the same path around the Sun. Nothing has come along that was strong enough to tell it to do otherwise. And this creates a subtle but important shift in how we think about causality. The cause of Earth's orbit is not something that happened once and then ended. It is something that happened once and never stopped mattering. The past is not behind the orbit. The past is inside it. Each lap Earth completes is not a repetition. It is a continuation. The path closes in space, but not in time. The motion is always new, but the reason it exists is old. That's why orbits feel timeless. They are not renewed, they are carried, and this has an unsettling implication. If orbits are memory, then changing them is not just changing position, it is rewriting history. To meaningfully alter Earth's orbit, you would have to inject a new memory, one strong enough to overwhelm the old one. A new pattern of motion, imposed violently enough that the previous record is erased. This is why orbital changes, when they happen, are catastrophic. Small nudges don't overwrite memory. They add noise. They wobble the path slightly, but the core pattern survives. To truly change an orbit, you need an event large enough to dominate the system's bookkeeping. That kind of event is rare. which is why Earth's orbit has lasted as long as it has. The universe does not easily forget. It prefers to carry forward what already exists, adjusting gently rather than erasing outright. This preference is not kindness, it is efficiency. Erasing information costs energy. So the orbit continues, not because it is protected, but because rewriting it would be expensive. And that brings us to the next natural question. If orbits are memory, and memory is hard to erase, then what are the limits? What kinds of changes are possible? And what kinds are effectively forbidden? At what point does the universe say, this path is too established to undo? That boundary between change that accumulates and change that overwrites is where the story moves next. There's a difference between changing an orbit and disturbing one. From far away, the difference can look small. A slight shift, a subtle wobble, a slow drift that takes centuries to notice. But physically, those two categories live on opposite sides of a boundary. A disturbance is when the orbit keeps being the same kind of memory, only slightly blurred. A rewrite is when the memory is replaced, and rewriting is expensive. You can feel this in your bones if you picture something familiar. Imagine a train moving at full speed down a track. Not a toy train, a real one. Hundreds of tons of mass committed to a direction. Now imagine you stand beside the tracks and place one finger against it, trying to stir it slightly. The train doesn't politely adjust. It doesn't care that you have intentions. Your finger doesn't change the path. Your finger breaks. This is what inertia feels like at scale. An orbit is that kind of commitment. Earth is a massive body moving at enormous speed around the sun. The motion is not a surface detail. It is the defining state of the system. If you want to change that state in a meaningful way, you are not nudging a point along a curve. You are trying to edit a conserved quantity. You are trying to change the energy and momentum tied up in Earth's trajectory. And those are not things that drift away by accident. They persist. They demand payment. Small influences can alter timing. They can twist orientation. They can make the orbit precess slowly, like a spinning top tracing a circle. They can trade tiny fractions of momentum between bodies over long periods, but the core motion remains, because the core motion is heavy. This is why the solar system is both dynamic and stable. It allows endless minor changes without losing its overall architecture. The details can evolve while the memory persists. To truly rewrite the orbit, you need one of two things. Either you need a force applied in a sustained, targeted way over a long time, something like a continuous engine capable of pushing a planet-scale object. Or you need a brief, violent interaction that transfers an enormous amount of energy and momentum instantly. In nature, the second is far more common. Close encounters, giant impacts, massive gravitational scattering events. Moments when bodies pass near enough to exchange a large fraction of their motion in a single episode. These are not gentle, they are system-defining. When a planet's orbit changes dramatically, it's not a quiet adjustment, it's a trauma. That's not a metaphor. It's a statement about how conserved motion behaves. To remove or add a meaningful amount of orbital energy, you have to put that energy somewhere else. The universe doesn't allow unaccounted edits, so a rewrite means another body must take the difference, which is why large orbital changes tend to come in pairs. One object gains, another loses. One is flung outward, another falls inward. One is captured, another is ejected. The system balances its books through exchange. This is also why the simplest way to stop Earth from orbiting is not to pull it inward. Gravity is already pulling inward. The simplest way would be to remove its sideways motion, to drain the orbital energy that prevents direct inflow. But how do you drain that motion? You would need a mechanism to absorb it, something like a planetary scale brake, a way to turn that coherent motion into heat, radiation, or the motion of other bodies. The solar system has no such brake. Space is too clean, too empty. There's no friction. There's nothing for Earth to rub against. No medium to dissipate the energy of its orbit. So the orbit doesn't decay the way motion decays on Earth. It persists. And that persistence is why the thumbnail paradox works. The viewer expects falling to be like falling on Earth, inevitable and final. But the finality of falling on Earth comes from the presence of a floor and a resistive environment, not from gravity itself. In space, gravity makes you fall, but it does not make you stop. Only interruption makes you stop. So the question, why doesn't Earth fall into the sun, is secretly asking, why isn't there an interruption strong enough to rewrite this orbit? And for Earth, the answer is simple and unsettling, because nothing has come close enough, massive enough, or misaligned enough to do it. Earth is not being held out of the sun. Earth is being left alone. This is where the solar system's stability takes on a different meaning. It isn't delicate balance. It's the absence of catastrophic rewriting events. Earth's orbit is stable because, since the early violent era of formation, the solar system has been relatively quiet in the ways that matter. The big exchanges are mostly done. The major scattering is mostly finished. The architecture settled into a configuration where large rewrites became unlikely, not impossible. Unlikely. That difference matters, because it means stability is not a law. It is a condition. As long as the condition persists, no massive near collisions, no close flybys by stars, no sudden destabilizing resonance shifts. Earth keeps its memory. It keeps falling. It keeps missing. It keeps returning. And now the paradox sharpens again in a new way. Earth doesn't fall into the sun because the solar system is not constantly rewriting itself. But what does rewrite orbits, even slowly? What small disturbances accumulate into real structural change? What hidden sculptures are still at work? Because even in a quiet system, exchanges still happen, just more slowly, just more subtly. And the most important sculptor in our case isn't the sun. It's the giant bodies sharing the same stage. That's where we go next. If you want to understand why Earth's orbit lasts, it helps to stop imagining a lonely planet circling a lonely sun. That picture is clean, it's also false. Earth is moving in a crowded gravitational room. The sun dominates, yes, but the sun is not alone in shaping what allowed motion looks like. Every large body in the solar system bends the geometry a little. Every mass tugs on every other. Most of those tugs are tiny, too small to matter on human timescales, but some of them are not. One of them is Jupiter. Jupiter is so massive that it doesn't merely orbit the sun. It modifies the sun's motion. The sun itself wobbles in response, like a heavy dancer adjusting to a partner's pull. That wobble is small, but it's real, and it ripples outward, shaping the entire system's gravitational rhythm. Now, Jupiter does not drag Earth around like a puppet. It doesn't need to. It does something subtler and, in the long run, more powerful. It repeats. A single small tug doesn't matter. But a small tug applied again and again, in the right pattern, becomes the sculptor. It becomes the kind of influence that doesn't look like force at all. It looks like fate. This is where the idea of resonance enters the story, not as a technical term, but as a human experience you already know. Think of a playground swing. If you give it one hard push at a random time, you might jolt it briefly, but the motion won't build. It will wobble and settle back into whatever it was doing. But if you push lightly, repeatedly, and always at the right moment, always in step with the swing's natural rhythm, the motion grows. Not because each push was large, but because each push arrived when the system could accept it. That is resonance. In space, resonance is the difference between a harmless tug and a slow, unstoppable rearrangement. Jupiter provides rhythm. Its orbit is steady. Its gravitational influence repeats. And when that repeating pattern lines up with another body's natural timing, the effects can accumulate over long periods, turning slight disturbances into meaningful structural changes. This is how the solar system can remain calm and still evolve. Earth's orbit is not static. It is constantly being very gently modified by the gravitational chorus around it. Most of those modifications cancel out or average away, but some align. Some persist, and here's where it gets strange. The solar system's stability does not come from everyone being perfectly isolated. It comes from everyone being coupled in a way that prevents chaos from escalating. It's like a crowd of people walking through a narrow hallway. If everyone moves randomly, collisions multiply. If everyone develops a shared flow, the crowd becomes stable even though every person is still moving. Jupiter helps enforce the flow, not by dominating every detail, but by shaping the environment in which details have to live. It carves gaps in asteroid populations. It defines zones where orbits become unstable. It acts as a kind of gravitational metronome that certain regions cannot ignore. You can see its signature most clearly in the places where the system is missing something. Empty lanes in the asteroid belt, where objects should exist but don't. Regions where repeated gravitational kicks have ejected bodies over time, clearing paths as surely as a plow clears snow. Those absences are not accidents. They are outcomes of repeated rhythmic nudges. They are the fossil marks of resonance. Now, Earth is not in one of those unstable means. If it were, we wouldn't be here. This is part of what makes the story quietly sobering. The solar system contains rhythms that can destroy orbits, and Earth survives because it lives in a region where those rhythms do not build catastrophically. Earth's orbit is stable, partly because it is out of tune with the worst resonances. That phrasing sounds artistic, but it's literal. The orbital periods, the distances, the masses, they combine to avoid a handful of deadly patents, but avoiding something is not the same as being immune to it. The solar system is not a locked sculpture. It's a living negotiation that has remained stable so far. Jupiter is part of that negotiation. It doesn't threaten Earth in the dramatic way people imagine, like a cosmic bully flinging planets into the sun. But it does remind us of something important. Big changes don't require impacts. They require persistence. The reason Earth doesn't fall into the sun is not just that its orbit is a balance. It's that nothing has persistently taken energy out of the orbital motion in a way that compounds. Jupiter, despite its size, mostly redistributes energy and momentum without destabilizing Earth. But Jupiter demonstrates that the system is capable of long-term sculpting. It shows that stability is dynamic. It's maintained not by stillness, but by an evolving architecture that keeps catastrophic pathways rare. And once you realize that, you stop asking whether Earth could fall into the sun tomorrow. You start asking the more accurate question: what kinds of slow changes, repeated over a long time, could eventually push a stable orbit into an unstable region? Because that is how systems change at scale. Not by sudden failure, but by drifting into a bad rhythm, into a pattern that starts to amplify instead of cancel. That possibility is not a prediction. It's a property of how gravitational systems behave. And it connects back to the deep theme we've been building all along. Earth orbits the sun because motion persists and the system's rhythms allow it. Earth doesn't fall into the sun because the solar system has, so far, avoided the patterns that would rewrite its memory. But that raises a problem. If these rhythms can sculpt paths over time, if resonances can clear lanes and destabilize zones, then how do we know our understanding of Earth's orbit is trustworthy? How do we know the future is predictable? That's the next rung on the ladder. There's a reason we speak about orbits with a kind of confidence we rarely use elsewhere in science. We talk about where planets will be next year, next decade, even centuries from now, as if we're reading a schedule. We send spacecraft through interplanetary space and thread them between worlds with timing so precise they feel almost arrogant. We tell the time by satellites that depend on the stability of their paths, and most of the time, it works. This confidence isn't optimism, it's bookkeeping. Orbital motion is governed by a handful of constraints that are brutally consistent. Energy doesn't vanish. Momentum doesn't disappear. Motion can be redirected, redistributed, exchanged, but it cannot be edited without payment. That makes the system, in a deep sense, conservative. It carries its own receipts, so when we predict orbits, we're not predicting whim. We're predicting what happens when you let those receipts play out. This is why Earth's orbit is not a fragile thing. It's a consequence of accounting that the universe keeps strictly. But here's where it gets strange. The same system that is predictable enough to land probes on distant worlds is also capable of producing long-term uncertainty. Not because the laws change, not because the equations become wrong, but because tiny uncertainties in the present can, under the right conditions, amplify into large uncertainties in the far future. This isn't mystical, it's structural. Picture a perfectly built mechanical clock. If it's isolated, protected from vibration and temperature changes, it keeps time beautifully. Now imagine placing that clock on a table that is gently, constantly shaking. Not violently, but persistently. Over short intervals, the clock still keeps time. But over long intervals, those tiny perturbations begin to matter. The drift grows. The future becomes fuzzy. The solar system is not a clock in a vacuum. It is a clock in a vibrating room. Every planet tugs on every other. Most tugs cancel. Some resonate, some accumulate. The system remains stable in the sense that it doesn't tear itself apart. But stability is not the same thing as perfect repeatability. This is why prediction has a horizon. For the near future, decades, centuries, the horizon is far away. Our models work extraordinarily well because the system doesn't have enough time to amplify small differences into dramatic deviations. But as you extend the timeline, the system starts to behave like a story with branching paths. Not because it becomes random, but because the details that decide which branch you follow become too small to know perfectly. The future becomes not unknowable, but statistical, and that reveals a crucial truth about why Earth doesn't fall into the sun. Earth's orbit is stable not because it is guaranteed by a simple rule, but because it lives in a region of the system where disturbances don't easily snowball into catastrophic rewrites. Over the timescales that matter for human civilization, the future is locked in tightly enough to trust. But the solar system is not a sealed machine. It is a long negotiation that can, in principle, drift. The difference between we can predict and we can guarantee is time. That's the subtle boundary. Predictability is not a property of the laws alone. It is a property of the laws plus the timescale you're asking about. This is why our confidence in orbital mechanics is both justified and limited. We can predict Earth's position very precisely because we have measured it, modeled it, and tested the models against reality again and again. We refine the numbers. We account for influences. We include the tugs of other planets. We correct for small effects. But the longer you go, the more you depend on details that cannot be known perfectly. Tiny uncertainties in initial conditions. Tiny unmodeled influences. Tiny chaotic interactions. Over long times, those become meaningful. It's like forecasting the weather. You can trust tomorrow. You can usually trust next week's general pattern. But beyond that, the exact path of storms becomes uncertain, even though the physics of air and water didn't change. The solar system is far more stable than weather, but the principle is the same. Short-term certainty, long-term fog. And that fog doesn't mean Earth is in danger of suddenly falling into the sun. It means something more subtle. The solar system is a living system, not a frozen diagram. It has a future, and that future is shaped by the same slow sculpting we've been talking about. We can trust the near future because the accounting is tight and the amplifications are slow. We cannot claim infinite certainty because there is no such thing as infinite precision, which returns us to the deeper point. Earth orbits the sun because motion persists. Geometry shapes paths, and the system's rhythms allow stable continuation. The reason we can predict that orbit is because those rules are consistent and the system's current arrangement is well behaved. But knowing the path is not the same as holding the path. Prediction is not control. The universe doesn't ask us whether we understand. It doesn't pause because we've mapped the motion. It continues. And if we want to survive, navigate, and build technology inside that continuing motion, we have to do what every successful spacecraft does. We have to work with the orbit, not against it. That's where the story starts to touch the real world in a sharp way. Not as trivia, but as proof. Because the most convincing argument that Earth doesn't fall into the sun isn't philosophical. It's the fact that we use the same physics to place machines in free fall on purpose, and they keep falling, missing, and returning, exactly as predicted. That's where we go next. If the idea that Earth is constantly falling still feels like a conceptual trick, there's a simple way to make it real. We use the same trick on purpose. We build machines, we throw them into space, and we place them in continuous free fall, not as a side effect, but as the entire point. And then we rely on that fall with enough confidence to build navigation, communications, and time itself on top of it. That's what a satellite is. A satellite is not up there because gravity is weaker. It's not floating because it escaped Earth's pull. That satellite is falling toward Earth the same way you would fall if the ground vanished beneath you. The only difference is that it's moving sideways fast enough that it keeps missing the ground, just like Earth keeps missing the sun. This is why the paradox in your thumbnail is not a paradox at all. It's the most practical feature of gravity that we know how to exploit. If you want an image that burns it into your intuition, don't imagine a rocket. Imagine a throw. Imagine throwing a ball forward. It travels and falls. Throw it harder. It travels farther before it hits. In a world with no air resistance, if you could throw it fast enough, the ground would curve away beneath it. The ball would fall forever, and yet never land. That's orbit. And this isn't just a mental picture. It is a historical one. People have used this exact image to understand orbital motion because it captures the truth that matters. Gravity doesn't need to be defeated. It needs to be timed. A spacecraft in orbit is not resisting gravity. It is cooperating with it. This cooperation is so precise that it becomes a kind of proof you can live inside. When engineers place a satellite in orbit, they are not hoping gravity behaves. They are betting on the bookkeeping of the universe, and the universe pays out. The satellite follows the predicted path. It returns over the same regions of Earth at predictable times. It remains in free fall until something interrupts it. A bit of atmospheric drag, a deliberate maneuver, a gravitational nudge. Notice how clean the story is. Orbit persists until interruption. That is exactly Earth's story around the sun. Earth's orbit persists because space is almost perfectly non-interfering. There's no thick medium to drag it down, no cosmic floor to stop it, no steady brake that drains orbital motion into heat. So it keeps falling, missing, returning. This is why the human instinct that things should fall down becomes unreliable the moment you leave the ground. Falling does not mean approaching an end. It means obeying gravity in the absence of support. And when you obey gravity without support, you become weightless. Astronauts don't float because gravity is gone. They float because everything around them is falling together. The station, the astronauts, the equipment, all of it shares the same free path. No one has a surface pushing on them. The sensation you call weight is the sensation of being prevented from falling. So in orbit, you lose weight not by escaping gravity, but by escaping contact. This is one of the most quietly profound truths in physics. The same phenomenon that makes you feel heavy is the phenomenon that makes you feel stuck. The moment you remove the interruption, gravity becomes invisible again. And we don't just use this for dramatic footage. We use it to run civilization. Consider GPS. You don't need to know the full details to appreciate what it implies. GPS depends on satellites maintaining predictable orbits and transmitting time signals. Your phone uses those signals, compares their arrival times, and triangulates your position. This only works because orbital motion is stable enough to model, and time is stable enough to measure. But there's a deeper layer. Because once you rely on satellite clocks, you are forced to confront something Earth's orbit has been whispering from the beginning. Time does not behave the same everywhere. Not perfectly, not universally. When you build a system that measures location by comparing time signals from orbit, you are building a system that forces you to account for reality's subtle rules. Rules about motion and gravity and how they shape time itself. The orbit is not just a path. It is a testbed for physics, and that testbed passes continuously. Every successful satellite mission is a small, repeated formation of the same core idea. Freefall is not failure. It is a mode, a stable mode, a predictable mode, a mode you can design for. The same physics that keeps Earth from falling into the sun is the physics that keeps satellites from falling back down in the naive way your instincts expect. That's why the paradox is so powerful as a thumbnail. It forces the viewer to confront the mismatch between intuition and reality. And then, once the mismatch was resolved, it leaves behind something stronger than a clever explanation. It leaves behind trust. Trust that the universe is consistent enough to navigate. Trust that motion can be predicted without being controlled. Trust that falling can be stable. But that trust comes with a boundary. Because while we can ride these paths, we cannot ignore the cost of changing them. Every satellite maneuver costs fuel. Every correction is an accounting problem. Every attempt to leave one orbit and enter another is a trade. And that raises the next question naturally, without any hype. If orbits are free paths that we can ride, how hard is it to leave them? Not metaphorically, not romantically, physically. What does it cost to stop falling in a loop and start falling away forever? That's where the story goes next. If orbiting is just falling in a loop, then leaving an orbit sounds deceptively simple. You might imagine it like stepping off a path. Like choosing not to follow the curve anymore. Like pointing a rocket outward and pushing hard enough to break free. That picture is comforting. It's also wrong. Leaving an orbit is not about direction. It's about history. When Earth moves around the sun, it is not just near the sun, it is carrying a tremendous amount of sideways motion. That motion is not incidental. It is the orbit. To leave, you don't need to stop falling inward. You need to stop returning. And returning happens because the sideways motion keeps redirecting the fall. So to escape, you must do something very specific. You must add enough motion that the path no longer closes. Not a push-up, not a shove, a way. A precise reshaping of velocity that transforms a looping fall into an open one. This is why escape velocity is such a misleading phrase. It sounds like a speed barrier. Like a wall you have to punch through. But escape velocity is not about overpowering gravity. It's about changing the kind of path you're on. Below that threshold, every fall loops back. Above it, the fall never returns. The sun doesn't suddenly stop pulling. Gravity doesn't turn off. Nothing dramatic changes locally. The only thing that changes is the future. You stop coming back. And here's where the cost becomes clear. Earth's orbital motion is enormous. It has been built up, conserved, and carried forward for billions of years. To leave the sun entirely, you don't erase that motion. You add to it. You pile new velocity on top of old velocity until the bookkeeping tips. That addition is expensive. Not because space resists you, space doesn't care. Not because gravity fights back harder. Gravity stays the same. But because inertia remembers everything. Every kilogram of mass carries its motion with it. To change that motion in a meaningful way, you must supply energy proportional to how much motion already exists. This is why rockets don't feel like engines of freedom once you look closely. They feel like accountants. Every burn is a negotiation. Every maneuver is a trade. Every trajectory is a compromise between what you want and what history already decided. This is also why most spacecraft don't go straight out. They spiral. They borrow. They steal momentum carefully from planets that can afford to lose a little. They surf the same gravitational currents that shape planetary motion, because brute force is almost never the cheapest option. Leaving an orbit is not a rebellion. It's a collaboration. And that collaboration only works because the orbits themselves are stable enough to be predictable. You can't steal momentum from something chaotic. You can't plan a future around a system that doesn't repeat. So the same stability that keeps Earth from falling into the sun is what makes escape possible at all. Slowly, carefully, and at great cost. This is another inversion worth sitting with. The universe doesn't trap you by force. It traps you by consistency. Once you are part of a stable pattern, leaving requires you to supply something new, something that wasn't there before. Energy, precision, timing, and even then, you never truly leave motion behind. You don't reach rest, you don't reach stillness, you just trade one inherited path for another. That's the quiet truth behind every deep space mission. Nothing ever escapes motion. It only changes whose motion it's carrying. So when you look at Earth and ask why it doesn't fall into the sun, the deeper answer is no longer about gravity at all. It's about commitment. Earth is committed to its path, because changing it would cost more than the universe has ever casually supplied. The orbit persists because it is cheap to keep and expensive to undo. And that's not a flaw. It's a signature. The universe is built to preserve what already works, and charge heavily for what tries to overwrite it. Which leaves us with one last turn before the conclusion. If motion is conserved, if escape is costly, and if stability comes from continuity rather than balance, then the orbit is not just something Earth does. It's something the universe allows and quietly insists on. That's the door we close next. At some point, every explanation reaches a place where adding more detail stops helping. You can keep refining the picture, talk about velocities, trajectories, perturbations, corrections, but eventually you realize the answer hasn't been missing information. It's been missing perspective. Earth does not orbit the sun because it is held there. It does not avoid falling because of a delicate balance. It does not remain safe because the universe is constantly adjusting it. Earth orbits because the universe allows motion to continue. That's the deepest layer. From the very beginning, the universe made a choice, not a conscious one, but a structural one. It chose to conserve, to carry motion forward, to let history persist unless something overwhelmingly strong intervenes. That choice echoes everywhere. It's why momentum doesn't vanish, why energy doesn't disappear, why time has a direction, why causes leaf effects that don't rewind. Earth's orbit is simply one expression of that rule. Once the planet inherited motion from the disk that formed it, there was no mechanism waiting to erase that motion gently. Gravity didn't oppose it. Space didn't resist it. Nothing smoothed it away. So the motion stayed. And once motion stays, paths emerge. Once paths emerge, repetition appears. Once repetition appears, stability follows. Not guaranteed stability, permitted stability. This is the crucial distinction. The universe does not protect outcomes. It protects continuity. If something is already moving in a way that doesn't contradict the rules, the universe does not step in to correct it. It does not ask whether the path is elegant or useful. It does not prefer stillness over motion or collapse over orbit. It simply keeps the books. Earth's orbit is what remains when nothing forces a change. And this explains why the idea of falling into the sun feels so intuitively urgent and yet physically wrong. Falling in space does not mean approaching an end. It means following a path. And the path Earth follows never ends at the sun, because it was never aimed there to begin with. The sun bends the path. Inertia extends it. History preserves it. That combination is enough. Once you see it that way, the orbit stops feeling like something precarious and starts feeling like something honest. Not safe in the emotional sense, but faithful to the rules it was born under. The universe is not constantly saving Earth. It is simply not interfering, and that, paradoxically, is what makes everything else possible. Because in a universe that corrected motion aggressively, nothing would last long enough to matter. Every structure would be temporary. Every pattern would decay quickly. There would be no long-term platforms for complexity, memory, or understanding. Continuity is what allows meaning to accumulate. Earth orbits the Sun because continuity won, and continuity, once established, is extraordinarily hard to break. That's the final, content-level truth. What remains is not explanation, it's reflection. So let's return quietly to the question that started all of this. Why doesn't Earth fall into the Sun? Because falling never meant what we thought it meant. Because motion was never erased. Because space never offered a floor. Because gravity never asked Earth to stop. Earth is falling here freely, continuously, along a path shaped by mass and preserved by history. The orbit is not a struggle. It is a permission granted long before there were oceans, long before there was life, long before anyone could look up and wonder why the sky behaved so calmly. All the planet does is continue, and that's the quiet boundary this reveals. The universe does not guarantee safety. It guarantees consistency. It carries motion forward. It lets paths persist. It closes no door unless something powerful enough forces it shut. Earth remains in orbit, not because it is special, but because nothing ever told it to stop. And the door closes softly there.